Alright, for our final unit, Unit 4, for the spring 2015, we're going to be talking about the last three chapters in our book, chapters 16, 17, 18. We recently got done talking about radical reactions and also talking about, in chapter 11, activation of alcohols and also oxidations. So now we're going to finish kind of our last set of functional groups. We're going to talk about carboxylic acids, so C double bond O's, right? Essentially carbonyls. In this particular, we're going to talk about carboxylic acid derivatives. Chapter 17 talks about aldehydes and ketones, and then 18 goes a little more into synthetic versions of these. So let's divide these families into groups. Basically, the big difference here is these are carboxylic acid derivatives, where Z is an atom that's more electronegative than carbon. So examples would be oxygen, an OH, an OR, a carbon like an ester, so a carboxylic acid here, an ester here, an amide. An amide would be a possibility. A chloride, an acid chloride. We can even have anhydrides. Nitriles are considered a derivative of carboxylic acids as well. The other type that's not in chapter 16 are Z here, right? Z is just a designation. So all these are derivatives of carboxylic acids. Z here being R and H, which would basically mean either a ketone or an aldehyde, right? So basically that's saying these can all be turned, or are, either can be turned into or are good leaving groups. Carbon and hydrogen are never going to be good leaving groups. That's the big difference. So we'll focus on these first. Similarities: the carbon of the carbonyl group is always delta plus. How delta plus is it depends on what's attached, but the carbon of the carbonyl is the electrophilic site always. So we do a little bit of nomenclature here. Go through this kind of fast. Again, nomenclature, how much we need to know is, enough to identify these things. C double bond O is called the carbonyl group. There's many different types of carbonyl groups. An acyl group is a carbonyl with an R group, which would be a carbon group. This is an acyl group. So generally speaking, we're talking about carbonyls. That's a C double bond O. And a particular type of carbonyl is an acyl. Again, breaking these down, these classes of carbonyls, this is in your class notes. And the biggest thing is here, they do not react all the same way. They don't react the same way. Right? And we wouldn't expect them to. Right? An OH is different than an OR, which is different than a chlorine. Right? If we think about a chlorine as a leaving group, right, a Cl minus, we would say is much more stable than, say, an NH2 minus as a leaving group. So that's the things we got to be thinking about when we understand how these react. And even more so, carboxylic acid, it can react as an OH. So there's a lot of things to think about. But all of these groups, the OH, the OR, the Cl, and these nitrogens, these amides, can be replaced by a nucleophile. And that's the key, right? Versus before, when it was just a carbon or an H, those are not good leaving groups. These can be leaving groups. So they can be substituted. Now the mechanism will be a little different than we've done before, but they can be substituted. So here are the other classes, the other H and R, right? These cannot be replaced by a nucleophile, right? Because H minus or R minus or C minus, they're not very good leaving groups, right? A good leaving group is something that's stable, right? We've seen the leaving group hierarchy before. H minus and C minus would not be very stable. They would not be very good leaving groups. Right? So all those ones before, the OH, the OR, the Cl, all the amide, NH minus, are good enough leaving groups to be replaced by a nucleophile. But again, it's a substitution, right? It's a substitution, but right, it's going to be different. So these ones do not have a good enough leaving group. So we'll wait till chapter 17 and worry about the aldehydes and ketones. Now here's a table that's in your book, and again, they're talking about basicity, which I think can sometimes get confusing. Just remember what you know, right? So here are the numbers of pKa, basically saying pKa tells us how good of an acid something is, right? So none of these are acids. They all have negative charges. They're talking about basically their conjugate They're conjugate acids. So these are all bases. But basically what this is telling us is Cl minus stable. Yes, it's a more stable leaving group than an OR minus, which is about the same. These are about the same. And again, NH2 minus is not a very good leaving group relative to O minus because O minus is more electronegative, right? Cl minus is big, right? So it's a better leaving group than OR minus. Those periodic trends we've done before. If you look down here, H minus and R minus, right? These are horrible leaving groups, right? H minus and R minus are super unstable, right? So those are not very good leaving groups. That's why these don't react in these substitutions. Kind of as we're working through this nomenclature stuff, another thing to remember, here's 3 different forms to draw a carboxylic acid. So here's a carboxyl group. That is just this essentially section right here to consider the carboxyl group. It contains the carbonyl and the OH for a carboxylic acid. Carboxyl groups can be drawn in different ways, COOH, CO2H. Right? Those are both, should recognize, and you see those as well. Some basic nomenclature for carboxylic acids. Up top, you have the systematic name and the common name. So systematic name is the IUPAC. That's actually one that kind of makes sense. Common names are things you just they're just known. So basically, it's back to methyl, ethyl, propyl, butane. Right? So methanoic acid, because there's 1 carbon involved, this is methanoic acid. Ethanoic acid has 2 carbons involved. Propanoic, 1, 2, 3 carbons involved, or 1, 2, 3 that way, and butanoic again. Acetic acid, you should know. Formic acid, you should know. Other than that, I'm not really interested in knowing the common names. Pentanoic, 1, 2, 3, 4, 5, right, and so on and so forth. I'm not worried about you knowing those. But make sure you do know formic and acetic. Alright, some basic nomenclature for carboxylic acids. The numbering, the systematic numbering, is 1, 2, 3, 4, 5, 6. So starting with the carboxyl group is the actual number 1 priority, so it has the highest priority. The other way they can number these is off of, if you consider, again, the carboxyl group, whatever's off that is considered the alpha carbon. So you can see alpha, beta, gamma, delta, epsilon. So if this whole group right here is our carboxyl group, the thing attached to it is the alpha carbon. Right? So this is the whole group, and the alpha carbon is attached to it. So that's alpha, beta, gamma, delta, epsilon. Versus systematic, where there'd be 1 carbon is with the carbonyl part. So it's a little different. All right, now to take this a step further, how would we do it systematic versus common? Most people, I mean, again, you should be able to do both of these. I'm not going to make you know tons of Greek, but if we zoom in on some of these, if we look at some of these, the systematic, the numbering, right, would be 1, 2, 3, 4. So it's butanoic acid, because there's 4. That's the main chain. There's 4 of them, right? So butanoic, it's an acid, so butanoic acid, that's the carboxylate part. And off the second carbon is a methoxy. The common name, you could also go alpha methoxy butyric acid, but I'm not going to put a lot to that stuff. Do understand where alpha, beta, and gamma are at, what positions they are. But if I gave you this name, right here, or this name, you should be able to draw the structure. Hopefully that makes some sense. Again, if you do another example, 1, 2, 3, 4, 5, right? The bromines off the third carbon, or the beta carbon, as it were, the same idea. Incorporate some rings. This middle guy you should know already, that's benzoic acid. So carboxylic acid piece of a benzene ring, benzoic acid, or benzene carboxylic acid. Here, carboxylic acid, the substituent off of that would be cyclohexyl. So cyclohexane carboxylic acid. Carboxylic acid is the main part. Again, carboxylic acid is the main part, and this time there's 2 of them. Note how they're drawn differently. The COOH, remember they could also be drawn CO2H as well. Another carboxylic acid derivatives are the acid chlorides. So that is essentially if there's this piece is considered the acid chloride piece. A couple different ways to name these. There's the oil, so ethanoyl chloride. So note the oil piece kind of here. Right? There's 2 carbons, so ethanoyl chloride or acetyl chloride is a common name. Again, if it's a bromide, it's a bromide. So 1, 2, 3, 4, 5. So it's pentanoyl for 5, oil, bromide, and there's a 3-methyl off of it. If you have a ring, again, cyclopentane, cyclopentane, carbonyl, chloride. Right? Usually I don't have people name a lot of these, but just so if you see them. Alright, so moving along, we're going to name some esters now. So we're going to naming esters with the O8 ending, the 8 ending. That's our suffix here, the 8. Carbonyl oxygen, carboxyl oxygen with an R group off the end here. So we have an R group off the end. So let's look at one like this. So it's last acetate, a common one we've seen before. So the 8 here, we have a phenyl off the oxygen, and we have a 3-carbon piece, right? So we end up with the phenyl part off the oxygen first, propane 1, 2, 3, O8, right? So propanoate. So it's actually an O here in front. That's how we name it. So again, here we'd have the methyl piece, right? That's off the oxygen, so that's right there. We have the parent chain here now. So how many carbons is that? That would be 1, 2, 3, 4. So butanoate. And there's a bromine, 3-bromobutanate off of that. Some carboxylate salts. I mean, just remembering these, and this is a metal, sodium, potassium. How many pieces again? This is 1 carbon, methanoate. Right, sodium methanoate. By putting the sodium in front, we know that it's been deprotonated. Ethanoate, carboxylate. Usually we go by the carboxylates as well. A little more clear. Again, a carboxylate is a deprotonated carboxylic acid. Right, this came from carboxylic acid reacting, right, and getting water out and then a carboxylate out. And here's a couple biological examples of these things. But this is a carboxylate. Lactones. Know a couple of these. These are interesting. These are going to use your... I like to use the common names for these, actually. A little easier actually than the systematic names. So if we take the 6-membered ring here, again, let's circle the part that matters. Right? And the alpha carbon, remember, is not the one attached to this oxygen. It's off of the whole group. So if the group I circled here is the whole group. We start off of the carbonyl carbon. So this is the alpha, beta, gamma, delta. So we call it delta lactone because this oxygen attaches back to the delta position. But we always start counting, right? We say alpha, beta, gamma, delta. And it's still delta lactone, but we got to indicate it's a methyl there as well. So the type of, this is a generic type of lactone. This is a gamma lactone because of alpha, beta, and then of course we have the gamma here. So it's a gamma lactone. Anything more than that, knowing if it's a delta, a gamma, or even a beta lactone, that's basically the amount I want you to know. You don't need